All right, these video notes are on solving exponential equations. And we're going to study how to solve exponential equations right now at the beginning of the unit, but we're also going to study how to solve exponential equations later in the unit, but using a different method. So the method for this set is going to be by changing bases. Later, we will learn how to solve exponential equations by taking logs. So for today, we're going to look at changing bases. So I'm going to start off with a very, very simple example, and then we'll do some more complicated ones. So the first example is, let's say we have the exponential equation 3 to the x equals 3 to the 7. When you look at a problem like this, it's very clear that x should be 7, because then you have 3 to the 7 equals 3 to the 7. And so you'd say, okay, x equals 7. But we're not going to look at equations that are quite that simple. So we're going to look at one now that's a little bit more difficult. So 2 to the 3x plus 1 equals 2 to the 8. So we can kind of use what we did on the previous problem to make sure that we can do this problem as well. So we said that if the base was 3 and the whole thing was equal, then the exponents must be equal as well. So even though this example feels a little bit less clear, we're going to do the same thing. We're going to say if the bases are the same, then the exponents must be the same as well. So I'm going to go ahead and say 3x plus 1 equals 8. And then I could subtract the 1 over, so 3x equals 7. And then I can divide the 3 over, so x equals 7/3. So that problem was a little bit more difficult, but still pretty simple. All right, so we're going to try another one. 2 to the 2x equals 8 to the 4th. So this is really getting into what we're going to zoom out. This is going to be what we're really getting into when we solve exponential equations by changing the base. So we know if the base of the number is the same, then solving for a variable in the exponent is pretty easy. But if the base isn't the same, then we want to change it so that it is the same. So what we're going to have is this little sheet that has not all of the exponents, not all of the bases with their exponents, but a lot of them. And so I have 2 and 8. So what I'm going to look for is I'm going to look in here, and I'm looking at the columns of what the numbers equal. And I want to try to find a column that has 2 and 8 in the same column. So if I look at that, I can see a 2 here and an 8 here. And these show up in the 2's column. So that means that when I change the problem, I want the problem to have a base of 2. So 2 to the 2x already has a base of 2, so I'm going to go ahead and leave that one. 8 does not have a base of 2, so I'm going to take the 8 out and I'm going to replace it with a 2 to the 3rd. So 2 to the 3rd, I'm replacing the 8 with 2 to the 3rd. It's still being raised to the 4th, so I'm still going to put the 4 right there. Now we have to remember our exponential rules. So if you have an exponent raised to another exponent, then you need to multiply the exponents together. So this gives us 2 to the 2x equals 2 to the 12. And at this point, this is like one of the more simple problems, and we can just say, oh, the exponents must be equal to each other. And so x equals 6. Okay, let's try another one. 64 to the 3x equals 4. So again, I'm going to look on the little sheet and I want to see where 4 and 64 are in the same column. And this is actually an interesting problem because it happens in 2 columns. You've got a 4 here. Let me go ahead and circle these. So you can do it this way, 4 and 64. So you could change the problem to have bases of 2, or you could use this and let the problem have a base of 4. And in this case, you'll only notice this with the 2's and the 4's. It doesn't happen like everywhere else in the chart. It's specifically with the 2's and the 4's. And you can do the problem either way and you will get the same answer. right? Some people prefer to do the 4s because they don't have to change as much sometimes, but it really honestly doesn't matter because you will get the same answer. All right, so what I'm going to do with this problem is, since I have one of my problems written already with a base of 4, I'm going to go ahead and leave it as a base of 4, and then I'm going to take the 64 and I'm going to change that one to be a base of 4 as well. So 64 was 4 to the third. It's still being raised to the 3x, so I'm going to keep that up there. And then this 4 will be easiest for me to look at if it has an exponent, and so I'm going to put that exponent of 1 in there. So now I can go ahead and use my exponent rules, and I know that I just need to multiply those exponents together. So I get 4 to the 9x equals 4 to the 1. And since my bases are the same, I can go ahead and just take the exponents and set them equal to each other. And so x equals 1/9. All right, let's do another one. So here we're going to have 1 over 243 to the 3n plus 3, and that's going to equal 27 to the 3n. So a lot of students will be scared whenever they see a problem with a fraction in it, but all the fraction means is that when you look at this little sheet, is that you have a negative exponent. That's all that it means. It doesn't mean anything scary. So if we look at the sheet, we're trying to figure out where 1 over 243 and 27 show up in the same column. And if you look at the sheet, we can see 27 is down here. My chart actually doesn't go up to 1 over 243, but if you can see that 3 to the positive fifth is 243, then 3 to the negative fifth would be 1 over 243, because you can kind of see they go in pairs. So 3 to the 1 is 3, 3 to the negative 1 is 1/3, 3 to the 2 is 9, 3 to the negative 2 is 1/9, 27, 1/27, 81, 1 over 81. And so 3 to the negative fifth would be the 1 over 243. So these are the two that I'm going to use, these two right here. And so that means that I'm going to take my parentheses and I'm going to rewrite it with a base of 3. So this is going to be 3 to the negative fifth, and I'm going to keep the exponent up here. And then 27 I'm going to rewrite as 3 to the third, and I'm keeping the other exponent up there. And so now I just need to do my exponential rules. So I'm going to keep the base of 3, but I know my exponents need to multiply together. And when I multiply a -5 times a binomial, I do need to distribute that -5. So I'm going to get -15n minus 15 equals 3 to the 9n. And now that my bases are the same, I can take the exponents and show that they equal each other. So to get my n's to one side, I can go ahead and take the 15n and add it to the other side. And 9 plus 15 is 24n. And then I can go ahead and divide my 24 over to the other side. So I have -15 over 24. And that's a fraction that can be reduced. I can divide the top and the bottom by 3. And so n is going to equal -5 over 8. Okay, we're going to do just one more example. Sometimes they do crazy stuff, like 2 to the 4th times 4 to the 9th equals, and it wouldn't be 9. I think that's supposed to be a variable a. I can't read my own handwriting. All right, so we're going to say 2 to the 4th and then 4 to the a equals 1 over 32. So whenever things start to get more complicated, you're still going to look at your bases and your exponents, but you're going to have to be more careful to remember what your exponential rules are. How do you do an exponent to an exponent? What happens if you have the same base but different exponents, all sorts of things like that. So that's all it's going to do, is it's going to make it a little bit more complicated with that, but you'll find that they're still pretty easy. So first we look at our chart and we have to look to see where 2 and 4 and 1 over 32 are in the same column. And I can see a 2 and a 4, and 1 over 32 doesn't show up, but 32 does. It's down here. And so that means that 1 over 32 would have been up here. So I've got a 2, a 4, and a 1 over 32. That's what I'm going to be using for this problem. So the base of 2 is going to stay, because we were in the 2's column, but 4 is going to have to change. It's going to have to change to 2 to the second. And then 1 over 32 needs to change to 2 to the negative fifth. And since that 1 over 32 doesn't have an exponent on it, I don't really need those parentheses around it. All right, so I have 2 to the 4, 2 to the 2a equals 2 to the negative fifth. And at this point, we can't just say, oh, our bases are the same, so we can get rid of them. We have to think about what happens if you have a base to an exponent multiplied by a base to an exponent. So don't write this in your notes, but I'm going to remind you of something. Most students have a hard time seeing it this way, but if I said x squared times x to the third, most of you would have no problem saying, oh, that's x to the fifth. And that's because if your bases are the same, then you add your exponents together. 2 plus 3 is 5. So over here, what we are going to write on our notes is that if we have a base of 2 and a base of 2, we just need to add the exponents together. That's 4 plus 2a. So at this point, we can say the bases are the same. Now I can just look at the exponents. And I'll go ahead and subtract the 4 over. So 2a equals negative 9. And then I can divide the 2, and so a equals negative 9 over 2.